Hello, everyone. Welcome to the webinar about running Kubernetes clusters on vSphere. My name is Jun Zhou. I'm the chief architect and founding engineer at Spectronauts. Please feel free to ask any questions during the presentation. And if time permitted, we'll have a Q&A session in the end. Joining me is Abhinav.
Hi, everyone. This is Abhinav Nagaraj. I'm a principal software engineer here at Spectronauts.
Thanks, Abhi. So in the previous webinar, we have shared the challenges to manage Kubernetes clusters and how ClusterAPI solve the challenges in all the different cloud environments. And we all know that on-prem infrastructure management is even more difficult than on the public cloud. So in this webinar, we'll talk about the specific challenges to run Kubernetes clusters on vSphere and the work that we have contributed to the ClusterAPI vSphere provider around this. The topics we want to cover today, including the HA support without cloud load balancer, and also how to running Kubernetes clusters across multiple feeder domains, and also with IPAM and the proxy support. In the end, we'll have a live demo. First of all, a brief recap about what is a ClusterAPI. The main goal of a ClusterAPI is to use Kubernetes declarative API with the customer resource definitions and custom controllers to manage Kubernetes itself. So if we take a Kubernetes cluster as a CRD, the CRD will just specify the cloud environment, like the Kubernetes version, how many master nodes, how many worker nodes. And then the customer controllers running in a management cluster will just trying to continually launch a new node and bootstrap the node, then join the node and eventually bring up the Kubernetes cluster in the target environment, whether it's a public cloud, private cloud, or bare metal. So these are the CRDs needed to create a Kubernetes cluster on vSphere. The user will just need to define a cluster resource together with the vSphere cluster resource, which capture the cluster level information like Kubernetes version, the cloud account, your vCenter information, and so on. And then together with the machine template, which would include the hardware configuration for your VM, like CPU memory, and so on. So internally, the ClusterAPI is using kubeadmin to do the bootstrap and configuration of the cluster. And we have a CRD called kubeadmin control plane, which is used to manage the control plane node, handles the kubeadmin init, the scaling, and etcd membership management. Then for workers, we have machine deployment. And you just need to specify the number of replicas together with the machine template information. And the controllers will create the underlying machines for each of the replica that you want to create. And this works pretty much similar to how Kubernetes manages pods and application deployment. The only difference is instead of talking to the Docker or Containerd to create a pod, these custom controllers will talk to vCenter to create underlying VM. So now let's look at our first topic, high availability. Just by Google HA for Kubernetes, most likely this will be the architecture that you will see. So we have a load balancer sitting on top of the 3 API servers, and all the worker nodes and other external clients, they were talking to either of the API server through this load balancer. On public cloud, it typically uses the cloud load balancer, like ELB. And for on-prem, there are many different options. There are open source solutions like HE proxy or Nginx. There are also commercial ones like F5 or A10. I think as an open source project, the ClusterAPI vSphere provider need to run in all the different like VMware environment. So a commercial solution may not be available in all the different setups. It's a natural choice to choose a open source solution as the default implementation. And that is what actually the ClusterAPI vSphere provider does. In ClusterAPI v1 Alpha 3 version, the vSphere provider introduced a new CRD called HE Proxy Load Balancer. It will create one separate additional VM running HE Proxy together with the data plane API. So when new control plane nodes are added or removed, the HE Proxy configuration is updated through the data plane API. With this new CRD, we can launch a HE cluster on vSphere, and all the control plane nodes, they can be easily rolled and upgraded. But one critical issue for this architecture is it is a single point failure. So if this load balancer VM is down, the whole cluster is down. So how to solve the issue of a single point failure? I think the most straightforward way is, of course, let's have more load balancers. Right? So when one load balancer is down, we have another load balancer still running. Then the problem comes is, how will the client know which load balancer to connect to? And one commonly used solution on-prem is virtual IP failover. So the two load balancer will share one virtual IP. The virtual IP could be attached to either one of them. With solutions like Keep Alive D, if one of the LB goes down, the virtual IP will be automatically moved over to the other one. So the client and the worker node, they just connect to the virtual IP. So they don't know like which load balancer they are connecting to. The only issue that is they may experience like limited downtime during the virtual IP move over. So with this, we solve the issue of a single point failure with the cost of bringing in two additional virtual machines to the stack and one additional component to configure and manage it, which is the Keep Alive D. I think this is still okay for virtualized environment, where launching two more VMs won't be a big deal. But what if for bare metal clusters? It will be very costly to have two additional bare metal machines just for load balancer. So can we make this simpler for both virtualized environment and bare metal? And that comes to KubeVape. So KubeVape is a new open source project to solve this specific challenge. Instead of using separate load balancer VMs, KubeVape runs as a static pod within the control plane node, just like any other like control plane component like API server, scheduler. All of them runs at a static pod within the control plane node. And then instead of using a separate solution like a Keep Alive D to do the VIP failover, it uses Kubernetes leader election to do the failover. And the leader election is already widely used within Kubernetes by all the different controllers. And also internally, it can also support load balancer mode. So even if the traffic only goes through to one of the master nodes through the virtual IP, internally KubeVape can load balance to other master nodes. So this is how now the default HE solution for ClusterAPI vSphere provider, the HE proxy load balancer based solution will be deprecated. Now let's look at another aspect for high availability, the feeder domains. In Kubernetes, the feeder domains are mainly consumed by the Kubernetes scheduler. Take Amazon as an example. When nodes are launched within a specific availability zone, the node will have labels with the region and zone information that the node is currently in. And also for the persistent volumes, if it's zone specific, Right? Again, like AWS, you cannot mount a volume to node in a different availability zone. So the persistent volume will also have a metadata to specify that it can only be attached to nodes within certain labels. With that information, the scheduler will make sure that the pod can spread across multiple AZs and volumes are attached to the pod that matching the affinity policies. In ClusterAPI, the same terminology, filter domain, is used to control where to place the VMs. For example, when you have a HA cluster with 3 control plane nodes, you want to distribute the 3 control plane nodes into 3 different AZs. So if one of the AZ completely goes down, your cluster still keep running. There are 2 mainly parts involved to achieve this goal. One part is the ClusterAPI generic controllers like cluster and KCP, and which they do not have the cloud specific knowledge. And then the other part is infrastructure provider like AWS cluster, which knows the AWS availability zones and the subnet and so on. Like we mentioned earlier, KCP, which is the kube admin control plane, is responsible to manage the control plane node. So it will need to get the AZ information from the infrastructure provider, AWS cluster, when it tried to create a new node for the control plane. The way it works is AWS cluster will generate the available feeder domain from the available subnet within the current VPC. So if you have a subnet created within AZ1A, right, then AZ1A will be one of the available feeder domains. And then this information will be populated back to the parent cluster object. And then the kube admin control plane will use those information to distribute the AWS machines into each of the 3 availability zones. So that is how the feeder domains are handled in AWS. And compared with the public cloud, there are some specific challenges in vSphere. First of all, the Kubernetes understands feeder domains in terms of region and zone, which vSphere does not have the concept. Right? In vSphere, you have data center, you have compute cluster, you have resource pools, but there is no region or zone. Secondly, for public cloud, the feeder domain itself can determine the placement of the VM, which is the availability zone. So you can place the VMs with the exact same configuration into different AZs. But that's not the case for vSphere, where different compute clusters will have totally different placement properties like resource pools and data stores, or even network and folders. And thirdly, the vSphere DRS, which is the distributed resource scheduler, could automatically move the VM around during the event like host failure or inside the maintenance windows. So the placement that is done by ClusterAPI need to make sure that it will not conflict with the DRS. I think the solution for this is an easy one. That means the ClusterAPI vSphere provider should not try to place the VMs onto any specific host. This also means that some of the use case we are not going to support. For example, we are not going to support to have a individual host at a feeder domain. So now let's look at the first challenge in detail, the region and the zone. To match what Kubernetes expects for feeder domains, vSphere introduced the region and zone concept for its cloud provider and container storage plugin, which is the CPI and CSI. The way it does is the vSphere admin can tag the infrastructure with the region and zone tags. then the tag category information will be configured into the CPI and the CSI. So when the Kubernetes nodes are launched within a certain computer cluster that is configured with a zone tag, the CPI will automatically label the node with the corresponding feeder domain information. And similarly for the volumes, the CSI will add the node affinity rules for the persistent volumes that is created within each of the feeder domain. I think with the tags as a loose coupling mechanism, the vSphere admin can create different topologies based on their specific requirement. For example, on the left-hand side, it shows a topology with mapping a data center to a region and multiple compute cluster within this data center to different zones. While on the right-hand side, it shows a topology with only one compute cluster within a data center and then can just use the data center as a zone. So with this already defined in CPI and CSI, the CAPV will just need to follow the same convention to define feeder domains with the tags with the region and zone topology. For the second challenge, for the placement, like I mentioned earlier, right? In Sphere, the different feeder domains will have different placement properties. So you cannot provide one VM template and place that VM into different feeder domains without changing the placement properties. The current ClusterAPI vSphere provider API kind of combine all the information needed into one VM clone template, which doesn't align with the new requirement. And during the last couple of weeks, we have worked with the community and the VMware engineers to come up with a proper solution for this. The proposal that we have is to have a clear separation between the feeder domains and the placement constraints. The feeder domains are defined by vSphere admin, right, which reflect the physical infrastructure fault domain. For example, the data center, the compute cluster, your host groups can be different feeder domains. On the other hand, the placement constraint, they are just metadata context, which added to the feeder domain to help vSphere decide where to place the VM. And the examples for placement constraints include resource pools, data stores, network, or even folder, those kind of information. So we'll have a couple of new CRDs. So the vSphere feeder domain CRD will define the region and zone that this vSphere setup has already configured. And the vSphere deployment zone CRD will refer to the feeder domain, then add the placement constraint of that feeder domain. These new CRDs are defined outside of a specific Kubernetes cluster. They can be populated by the admin or can be managed by a separate controller, which have higher privileged permission to do the, for example, auto discovery, the validation, and even configuration. So take this diagram as an example. For a vSphere setup with the 3 compute cluster, there will be 3 zones with the 3 feeder domain defined. And each of the feeder domain will have different resource pools and data stores, which is defined within this deployment zone. And the cluster will just refer to whatever deployment zone that they choose to use. And all the information will be eventually populated back into the VMs, which is created within the 3 different feeder domains. So this is the link of the proposal that we have to the ClusterAPI. Feel free to take a look if you are interested. That's it for the feeder domain. For next, we will switch it to Abhinav to talk about an IPAM support in ClusterAPI vSphere provider.
Thanks, Jun. Static IP, as we know, is an IP address that is statically configured for a device instead of one that is assigned by a DHCP server. It's called static because it never changes versus a dynamic IP address which can change over time. The cluster API for vSphere provider by default uses DHCP as the IP allocation type, but it also has an option to accept a specific static IP for every machine in the cluster. The only requirement, though, is for these IPs to be pre-allocated and available to the user before launching the cluster. This brings up some concerns on the practical implications of this method. For example, what if the static IPs for the cluster nodes cannot be manually pre-allocated? Even if pre-allocated, what happens when the cluster is scaled up? How do we now procure more IPs and configure them to the newly launched nodes? Or what happens if the cluster is scaled down? Can we now reuse the IPs of these deleted nodes in the future? Here, we are still talking about a single cluster, but what if you want to automate the management of multiple such static IP clusters? All of the above questions lead to one obvious answer, which is IPAM, or IP address management. The question for us was if we actually wanted to build a new tool to manage the allocation and administration of these static IPs. But as we know, enterprise IT teams today already use a variety of IPAM tools. Some of the popular ones are Infoblox, SolarWinds, BlueCat, and Lightmesh. These tools already reduce the network operating costs and eliminate configuration errors along with the associated downtime. Therefore, providing the flexibility to integrate these with the SpectroCloud platform was one of our key requirements. The solution we came up with has three parts. First, to make changes in the cluster API provider vSphere, changes to identify that the IP allocation type for the cluster is static IP and hence wait till the static IPs are allocated. Once allocated, to configure the IP to the intended network device on the intended virtual machine. Second, to provide a default out-of-the-box solution for IPAM, which accepts a static IP pool without any external dependency. For this, we use an existing open source project called Metal3.io. Third, to have an IPAM integrator in our platform, which not only supports the default IPAM, but is also flexible enough to be expanded to allow other integrations like Infoblox. This consists of a custom Kubernetes controller, which at the high level reads the vSphere cluster API resources to fetch the configured IP pools and allocate an IP from the pool. And this is for every new machine that is provisioned. On a scale down or delete operation, the IP allocation is returned back to the IP pool. We've currently open sourced this IPAM integrator project and have plans to integrate more IPAM solutions. When it comes to production environments, we may have restricted access to the internet, and the network traffic, in which case, is directed through an HTTP or HTTPS proxy. A proxy or a proxy server, as we know, is a device that acts as a gateway between a local network and a large-scale network such as the internet. The environment variables HTTP proxy and HTTPS proxy are used to configure the proxy server endpoint, and no proxy is used to define the list of network seeders, host names, domain names, etc. that should be excluded from proxying. We know the no proxy values that are required at minimum for any Kubernetes cluster with proxy configuration. This list could include the local host, the default Kubernetes service, or .cluster.local, which is a regular expression to skip proxying for the cluster domain. In addition to these, the vCenter endpoint and the VM or node IP seeder may also need to be added to the list. Also, there might be some requirements requirements specific to the network configuration or the applications running on these clusters. So allowing an option to customize the no proxy becomes an absolute requirement. All of these proxy configurations are available as environment variables, both inside the host and also in the pods running on these hosts. For example, in the Linux host, a system-wide proxy is set for all the Linux users by configuring the environment variables in scprofile.d. This would enable tools like wget and curl to reach out. Additionally, based on the container runtime that is being used, like Docker or Containerd, the proxy settings need to be set in the runtimes configuration. And this is to enable container management operations, like, for example, pulling the container images with a public endpoint. Once the containers are launched, the applications running in these may have the requirement to reach out to the internet. So when the application pods are launched, the proxy environment variables need to be injected into every pod that has a requirement to reach out. The brute force option is to have hard-coded environment variables values in the deployment manifest. But since this is not practical, we need a way to dynamically inject these. And there's several ways of achieving this. One of the options we chose was pod presets. So what is a pod preset? A pod preset is a Kubernetes API resource for injecting additional runtime requirements into a pod at creation time. This is done using label selectors to specify the pods to which a given pod preset applies. With this, we just need to define a single proxy pod preset and have the proxy label configured in the deployment manifest that require proxy. Once the proxy settings are available as environment variables in the pod, any application running in the pod can read these environment variables. One of the common use cases is applications using HTTP clients that make calls to the internet. There are also a couple of common challenges with applications. Some applications like Portworx, for example, have very specific domains like KVDB. In such cases, each namespace may need additional no proxy settings. Also, a lot of services communicate with other services by directly using the service name. And obviously, these internal calls need to skip proxying. So as a best practice, if services use the suffix .svc, then this regex can be added to the no proxy list to solve the issue. So with this, let me share my screen for the demo, and we can look at one of the clusters to go over some of the points that we discussed in the presentation. So here I have a simple deploy script. Let me first deploy the script. So if we look into the script, this is basically a simple script which is creating a simple kind cluster, applying a bunch of required secrets, applying the backend, and a couple of spectro-specific CRDs. So if we look into each of these CRDs, first one is the Spectro Cluster CRD, the spec for which defines the cluster profile template, which internally has a bunch of layers. So these layers could include the OS layer, the Kubernetes layer, the CNI, the CSI, and one or more additional add-on layers. Here, for example, we have the Prometheus operator as the add-on layer. The second CRD is the vSphere Cloud Config CRD. If you look at the spec, initially we allowed the option to select the IP allocation type. Here, for example, that's selected as static IP. The control plane endpoint is of type VIP or virtual IP, and the host is left empty. Like we saw in the presentation in static IP mode, the IPAM integrator actually picks an IP from the IP pool and allocates that to the control plane endpoint. The machine pool config defines a list of node pools. Here, for example, we have one master pool and a couple of worker pools, worker pool 1 and worker pool 2. And each of the node pools internally define placements or failure domains. Here, for example, this master pool has two placements, one on compute cluster vSAN cluster, and the second on compute cluster test cluster. And this master pool of size 3 will have the 3 nodes distributed across these two placements. Similarly, the worker pools have their own placements defined. Additionally, in static IP mode, there are IP pools defined for each of the node pools. The ranges for these can be defined in a couple of ways. Here, for example, we have a subnet CIDR defining the IP range. whereas in the second IP pool, we have a start and an end IP to define the range. This, along with the network prefix, the gateway, and the list of name servers, completes the definition of an IP pool. At minimum, each node pool requires at least one IP pool in static IP mode, but multiple such IP pools can be added at any point in the cluster lifecycle. So if you look at this cluster, it's still coming up. So in the meanwhile, we can look at a cluster that's already running. This cluster has a similar configuration. It's running in static IP mode, and the machine pool config has a master pool with two placements on cluster 1 and a second one on cluster 2. Similarly, the worker pool has two placements on cluster 1 and cluster 2, and each of the node pools are of size 3. So if you look at the pods, we saw in the presentation how HA is achieved using kubevip, which manages a virtual IP address for the cluster. If you look at the pods for these are static pods. These are static pods running on each of the control plane nodes. If you look at the logs of one of these, we see that one of the master nodes is elected as the leader for the load balancing. And if this node crashes for some reason, then the VIP is inherited by another master, which will then act as the leader. So in this case, this particular master node ending with LQ is assuming the leadership. So if we look at the list of nodes, we have 3 control plane nodes and 3 worker nodes. So this was the elected leader. If you look at the first master node, it has a single IP address ending with 177. The second master node similarly has a single IP address ending with 175, whereas the third master node, which was selected as the leader, will have an additional VIP or a virtual IP address ending with 174. Now, if we SSH into this master node, we can see that a single interface ETH0 has 2 IPs associated with it, one of them being the virtual IP address. After HA, we discussed IPAM, where we discussed a couple of pods associated with IPAM. One was the IPAM integrator project, k8s static IP, which is open source. And this supports a default IPAM solution, which is the Metal 3 IO. So for every IP pool definition that we saw in Cloud Config, an IP pool object is created. So if we look at the list of IP pools, now there's one IP pool created for every IP range that was defined in the config. And if we get into one of these IP pools, we see the same range that was defined in the config. And the status for this is showing the IPs that are already allocated from this IP pool and for these particular vSphere resources. So every time a vSphere resource requests for an IP, an IP claim is created by the IPAM integrator. An IP claim is basically just a request requesting an IP from this IP pool. And once the request is fulfilled, an IP address object is created. So if you look at one such IP address object, we see the claim for which this address was created. So an address was picked from this IP pool for this particular vSphere resource. In this case, it's a vSphere machine. And the finally allocated IP address was 10.10.185.0. Finally, we discussed proxy port presets as a means for achieving proxy. So if you look at one such proxy port preset, we see the list of environment variables, the proxy environment variables, HTTP, HTTPS, and no proxy, and match label as the selector. So any pod with this particular match label will have these environment variables injected into the pod. So if we pick one such pod, we see this particular pod has the proxy label, and it has a couple of containers, and each of the containers in the pod has these environment variables injected into the container, and any application running in these containers can then make use of these environment variables. So this is sort of what we had for the demo. Jun, back to you.
Thanks, Abhi. I think that is all the presentation that we have, and we still have time, and we're happy to take any questions.
All right. Well, folks, thanks for joining us. Really appreciate it and hope you guys have a fantastic day.
Thank you.
Thank you.